What you are about to hear isn't speculation or entertainment-driven science. It's something far more significant. This is the most important structural development since the object known as 3I Atlas was first spotted entering the inner solar system. New high-resolution orbital data has just been released, and what appears in these images is not another blurry coma or random cloud of dust and gas. What's inside these images is a geometry so precise, so mathematically rigid, that it challenges the very limits of standard comet physics. At first glance, everything might seem normal. The familiar diffuse glow, the bright halo surrounding the object, and the soft cloud of scattered light all appear like a typical comet. This is a visual signature we've seen thousands of times before with other cometary bodies. But here's the catch. That glow is deceiving. It's a trap. It masks the real structure beneath, making us see only part of the picture. When astronomers removed the typical cometary symmetry, they stripped away the circular noise, peeling back the light, layer by layer like fog, lifting from a distant mountain. What emerged was something completely unexpected. It wasn't chaotic, it wasn't turbulent, and it wasn't random. What emerged was order, a pattern, a structure, a configuration that shouldn't exist in a naturally occurring, thermally stressed comet. Until now, we've always assumed that when objects like comets come close to the sun, they are simply dust and ice reacting to extreme heat, sublimating into gas, and forming irregular patterns. But this is different. And this difference has forced astronomers to question everything they thought they knew about how comets behave. There's no question that what we're seeing goes beyond the familiar physics we've relied on for decades. Last week, a rare alignment of celestial bodies allowed for the clearest and most precise geometric view of 3I Atlas that we are likely to get during its entire journey. For the first time, astronomers captured data that reveals this object in a way that pushes against the boundaries of what we once considered possible for a comet. And the implications of this data, they could be far-reaching. This alignment, this rare window of observational clarity, has given us a glimpse of 3I Atlas that removes much of the distortion and noise that normally complicates our understanding of distant objects in the solar system. Whatever 3I Atlas truly is, the data collected in this cleanest of views might change our entire interpretation of what we are seeing. The clarity of the images we now have strips away the ambiguity that has plagued this encounter and points towards something far more extraordinary than we ever expected. This data is forcing us to rethink what this object is. Is it still a comet, as we initially thought? Or does it represent something far more complicated and unusual than we've previously believed? What's happening now isn't just a random coincidence or an observational anomaly. It's a clear signal that something fundamentally different is at play. Astronomers now face a choice: continue applying the old models or acknowledge that 3I Atlas might require a new set of scientific rules, one that challenges the traditional boundaries of our understanding. In the coming days, as more data is collected, we may find ourselves on the brink of a groundbreaking revelation. At first, the images of 3I Atlas looked exactly like what we expect from cometary physics: a bright coma, a diffuse hail of dust and gas, and a glowing cloud that's formed by sublimating ice and solar heating. These are the same visual features that have been observed in thousands of other comets. However, as astronomers dug deeper, they realized that this brightness was merely a facade, a form of optical camouflage that hid the true structural details beneath it. To uncover the hidden nature of the object, astronomers applied a technique called rotational gradient processing. This method is designed to mathematically cancel out anything that appears perfectly circular or symmetric. The idea is simple: rotate the image and subtract it from itself. Anything that is naturally round, such as the usual cometary coma, disappears, leaving only the irregular features that cannot be explained by symmetry. What this technique revealed was astonishing. The coma the usual cometary feature, vanished. But in its place, there was no randomness or turbulence. Instead, there was geometry. Three perfectly defined mini-jets appeared in the data, arranged in a symmetric triad, spaced exactly 120 degrees apart. This wasn't an anomaly or a random pattern. It was a rigid, stable configuration that repeated consistently over time. What's even more fascinating is that this pattern wasn't a one-time fluke. The same processing technique was applied to multiple high-quality observation datasets spanning nearly 2 months from late November to January. In every single dataset, the same configuration appeared with the same 120 degrees separation, the same stability, and the same symmetry. This persistence over weeks of observation was not random. It suggested that there was a deeper underlying structure to the object. The stability of this triadic structure implies that the jets are not temporary surface features created by random outgassing or volcanic activity. Instead, they appear to be deeply anchored within the object's structure, suggesting a highly organized internal configuration. Natural cometary bodies under thermal stress typically exhibit chaotic and irregular behavior, with jets that shift and change position over time. But 3I Atlas is different. Its geometry remains anchored, rigid, and stable, even as the object continues its journey through the solar system. The symmetry doesn't change, and the pattern holds firm. This raises more questions than answers. But it gets even more intriguing. Astronomers are not observing 3I Atlas in 3 dimensions directly. What we see is a 2-dimensional projection of a 3-dimensional object. This matters because random, chaotic jet distributions in 3-dimensional space almost never project into perfect symmetry, especially when observed from different angles. As Earth, the Sun, and 3I Atlas move relative to one another, the viewing angle changes continuously. If the jets were randomly placed fractures or volatile pockets, their apparent angular separation should fluctuate and distort as the object moves. But that's not what we're seeing. Instead, the geometry of the jets remains remarkably stable, regardless of the viewing angle. The 120 degrees symmetry persists across multiple observations, suggesting that the symmetry is not just an artifact of perspective, it's intrinsic to the object itself. This consistency implies that 3I Atlas's jets are arranged in a real, intrinsic, geometric configuration, likely organized around a rotational axis or a stable structural plane. In other words, the symmetry we're seeing is not due to where we are observing it from. It's an inherent part of the object's structure. This is a critical distinction. If the jets were simply random features, we would expect them to appear different depending on our vantage point. But the fact that they maintain this precise symmetry, despite changes in observation angles, indicates that the object's internal structure is highly organized and stable. This transformation from a random feature to a rigid structure changes the way we interpret the object. It suggests that 3I Atlas is far more complex than a simple comet, and its internal organization may be unlike anything we've seen before in the solar system. The question now is, what is the nature of this internal structure? Could 3I Atlas be an entirely new class of object, one that challenges the conventional models of cometary bodies? The more we observe, the more it seems that our traditional understanding of comets and small bodies in the solar system is insufficient to explain the behavior of 3I Atlas. Now, let's dive into the rotational dynamics of 3I Atlas. The object's rotation period has been inferred to be about 7.1 hours. For an object of this size, rotating that quickly generates significant centrifugal forces. These forces, combined with the sustained mass loss from the jets, should push the object toward fragmentation or at least visible deformation. Yet, despite these extreme forces, no such breakdown has been observed. The object remains structurally coherent and stable, which is another anomaly that defies conventional comet models. The behavior of the object is smooth and regular, not chaotic. The jets don't shift or migrate as we would expect from a body undergoing thermal stress. Instead, they remain anchored, their geometry stable over time. This raises a fundamental question: what's preventing 3I Atlas from fragmenting under the forces it's experiencing? In a typical comet, especially one of this size, rapid rotation and mass loss would create the conditions for the object to break apart. The centrifugal forces generated by such rapid rotation, combined with the ongoing outgassing, would normally destabilize the object. Yet, 3I Atlas defies this expectation. The fact that it remains intact, with its geometry and structure stable over weeks of observation, suggests that the object has a level of internal cohesion far beyond what is normally expected for cometary nuclei. This could mean that 3I Atlas has a mass distribution or internal structure that counteracts the destabilizing forces acting on it. Perhaps it's not a loose rubble pile held together by weak gravity, as we once thought. Instead, it could be a more robust, resilient body, one that has the strength to withstand the forces acting on it as it continues its journey through the solar system. This level of structural integrity challenges the very foundation of our understanding of cometary bodies. For years, scientists have assumed that comets are loose aggregates of ice and dust, weakly held together by gravity. 3I Atlas seems to be rewriting the rules. It's behaving in ways that standard models can't easily explain, and it forces us to rethink how we classify and understand objects in our solar system. Is 3I Atlas an exception, or does it represent a new class of object entirely? Now, let's focus on a key moment in the observation of 3I Atlas. On the 22nd of January 2026, a rare geometric alignment between the Earth, the Sun, and the object occurred. This alignment allowed astronomers to observe the object with unprecedented clarity, reducing the projection effects that typically complicate the interpretation of celestial bodies. This moment provided the clearest view of 3I Atlas that we will likely get during the entire encounter, and it offered a chance to observe its geometry without the distortion caused by perspective. In this rare alignment, the Earth, the Sun, and 3I Atlas became nearly collinear. This minimized projection distortions and revealed the object in its truest form. The opposition effect, when the sun's light illuminates the object from directly behind, further enhanced visibility by reducing shadows and increasing the signal-to-noise ratio. This allowed astronomers to detect faint structures that had previously been obscured by darkness and distortion. The opposition effect also sharpened the edges of the object, making fine details more visible. This was an observational window that won't come again. It's the best chance we have to study 3I Atlas in its most revealing phase. During this period, weak structures became brighter, and finer details became sharper. If there were substructures within the jets or other hidden features, this was the time when they would become visible. Astronomers knew that in less than 24 hours, the cleanest geometric view of the object would occur, and once this window closed, clarity would diminish. After that, the object would continue its outward journey, and observation conditions would worsen. For scientists and astronomers, this alignment was crucial. It allowed them to test the theories they had developed about the object's internal structure and behavior. If the symmetry of the jets persists during this phase, if the object maintains its stability under the most revealing conditions, then this will be a significant milestone in our understanding of 3I Atlas. The alignment strips away many of the excuses and uncertainties that have plagued previous observations. For the first time, the object's true geometry can be observed with minimal distortion, and we will finally have a clearer picture of what's really going on inside. Now, with the alignment completed and the clarity of the data at its peak, we are left with an essential question: what will this next set of observations reveal? If the symmetrical jet structure persists under these ideal conditions, if the oscillations remain coherent, And if the jets maintain their precise spacing when we see 3I Atlas in the most revealing angle, then we will be faced with a profound realization. This is no longer about speculation or theories. It becomes a constraint, a firm boundary on what explanations are still plausible. Science doesn't advance by solving mysteries alone. It progresses when uncertainty narrows into a clearer set of possibilities. This moment is significant because it's not about confirming the extraordinary, but about forcing precision. The data demands that we follow it, even when it leads us away from our comfortable assumptions. This is a rare opportunity for science to strip away the noise and focus entirely on the geometry, the pure, undistorted geometry that will define 3I Atlas. What makes this moment so crucial is that we are no longer dealing with an isolated anomaly or a fleeting observation. The structure and stability of the object have held steady despite weeks of thermal stress, changing illumination, and varying observation angles. This kind of persistence in symmetry is something we rarely see in natural celestial bodies. What we are witnessing is not random behavior, but an organized, dynamic system. This is a moment where science will either need to accept that its current understanding is incomplete or be forced to revise the models that have guided us for decades. In the coming hours, we will finally have the chance to see the object under the clearest and most revealing conditions it will ever be observed in. If the jets remain stable, if the geometry of the object continues to align as it has, then the debate will shift. The question will no longer be about what 3I Atlas might be, it will be about what the geometry allows it to be. This is the turning point. The patterns that we've observed so far suggest that 3I Atlas could be something far more complex than a simple comet. It could be part of a completely new category of objects that doesn't fit into the conventional models we've built over centuries of study. The geometry we are witnessing challenges everything we thought we knew about the behavior of small solar system bodies. If you want to stay on top of this groundbreaking discovery and witness the unfolding analysis, make sure to like this video and share it with others who value evidence over speculation. Subscribe to stay updated as we continue to analyze the data, and comment below with your thoughts on what the most conservative explanation is that still fits all the data we have so far. Because the conversation is no longer about what we want 3I Atlas to be, it's about what the geometry, the data, and the structure allow it to be. The universe is giving us a rare chance to peer into the unknown. Let's make sure we don't miss it.